Across thermal pitch darkness, a 70-ton steel monster surges forward with terrifying speed. The M1 Abrams main battle tank leaps from 0 to 20 miles per hour in under 7 seconds across soft desert sand. It accelerates without the deep, telltale rumble that enemies expect from heavy armored vehicles, earning a chilling reputation on the battlefield as whispering death. Rather than emitting the low vibration of a massive diesel engine, the war machine releases a high-pitched jet-like whine. Its sudden breakout from total stillness creates immediate panic, as target acquisition systems fail to register the approaching threat before it closes the distance. This silent approach gives the vehicle an unprecedented tactical edge during night operations. At the mechanical heart of this extreme mobility is the Honeywell AGT1500 gas turbine engine. Delivering 1,500 shaft horsepower directly into the transmission, this engine produces an incredible 3,750 foot-pounds of torque. Unlike conventional diesel power plants, the turbine generates maximum twisting force the instant the driver hits the throttle. Traditional tank engines require time to build boost and climb the revolutions curve before delivering full power to the tracks. The AGT1500 gas turbine bypasses this physical limitation entirely by maintaining continuous airflow through its power core. This continuous energy state allows the Abrams to surge out of danger or position for a shot with zero lag. This revolutionary setup was born from a high-stakes decision during the 1973 M1 tank trials. Army commanders demanded unprecedented speed and agility to counter numerically superior Soviet armor divisions massing in Eastern Europe. Chrysler Defense made a radical move, betting the entire program on a jet-derived turbine instead of safe, proven diesel technology. General Motors proposed a traditional diesel system, but Army leadership chose the high-risk turbine gamble. Chrysler proved that the gas turbine offered a power-to-weight ratio that diesel could not match. Winning this contract fundamentally shifted American armored warfare doctrine toward extreme speed, rapid repositioning, and immediate lethality on the modern battlefield. The structural anatomy of the Honeywell AGT1500 reflects cold, analytical precision. The power pack integrates a twin-spool axial and centrifugal compressor, a single combustor, and a three-stage turbine into a single compact unit. Weighing just 2,500 pounds, this modular assembly transformed how military mechanics service heavy armor under fire. Because the entire engine is designed as a unified power pack, ground crews can pull and replace a damaged turbine in under an hour. In high-intensity combat, this rapid field replacement keeps tanks fighting on the front line, while diesel-powered vehicles sit disabled in rear repair bays, waiting for complex overhauls. Paired with the Allison X1100 3B hydro-mechanical transmission, the compact turbine reshaped tank design priorities. Standard 1,500 horsepower diesels required massive engine compartments that consumed valuable internal volume. By shrinking the power pack footprint, designers created extra room inside the hull without increasing the vehicle's outer size. That saved space translated directly into life-saving survivability for the four-man crew. Engineers redirected the extra room to install thicker front composite armor and isolated fuel stowage capable of holding JP-8 military fuel. The radical engine choice ultimately produced a 70-ton main battle tank that shielded its soldiers behind unmatched armor while outrunning every threat on the field. Moving from structural hull gains to engine operation reveals a daunting reality. High performance demands colossal air consumption. At full throttle, the AGT500 ingests over 14,000 cubic feet of fresh air every single minute, Drawing in such massive atmospheric volume means the engine acts as a giant vacuum on the battlefield, inhaling toxic dust, fine sand, and debris that would instantly destroy delicate high-speed turbine blades. To keep the turbine spinning in harsh operational environments, engineers designed an aggressive multi-stage filtration system known as the vane-type air cleaner. Before foreign particles can reach the engine intake, swirling vanes force incoming air into tight vortices, flinging heavy dirt outward through centrifugal force. Automated pulse jets then blast short bursts of compressed air backward through primary filter barriers, purging trapped debris continuously without requiring tank crews to stop or open the engine bay. Once past filtration, clean atmospheric air enters the cold section compression core, embarking on a high-energy thermodynamic cycle. A twin-spool architecture divides the mechanical load, forcing incoming air through 5 sequential stages of axial compression before funneling it into a single centrifugal compressor stage. This hybrid arrangement compresses intake air down to a fraction of its original volume, achieving a total pressure ratio of 14.5 to 1. Maintaining smooth airflow through this mechanical crucible during violent throttle shifts presents an extreme physical challenge. When a driver slams the accelerator to evade incoming fire, rapid pressure fluctuations inside the engine housing risk triggering catastrophic compressor stalls. Variable inlet guide vanes automatically tilt in response to real-time operational loads, redirecting incoming air angles instantly to sustain stable pressure and prevent flameouts. The compressed air then blasts into a single reverse flow annular combustor, the thermal heart of the AGT1500. Fuel atomization nozzles spray finely misted fuel into the chamber, creating a continuous combustion flame that drives internal gases to scorching temperatures. The engine's unique combustion design provides extraordinary multi-fuel versatility, allowing the Abrams to run reliably on standard JP-8 military jet fuel, DF2 diesel, marine diesel, or even high-octane aviation gasoline. Crucially, switching between these radically different fuel types requires no manual recalibration or mechanical timing adjustments by ground crews. Advanced fuel metering valves automatically adjust injection rates and atomization patterns based on fuel density and ambient temperature. Whether pulling from airbase fuel bladders or captured commercial diesel stocks, the combustor burns fuel cleanly, giving armored commanders unprecedented logistical flexibility across unpredictable supply chains. Downstream from the combustion chamber, hot expanding gases drive 2 separate mechanical spools. The first high-pressure turbine powers the compressor stages to sustain continuous engine operation, while remaining gas energy streams into a 2-stage free power turbine. This free power turbine is completely decoupled mechanically from the front compressor assembly, acting as a fluid coupling directly connected to the transmission input shaft. This mechanical independence creates a devastating tactical advantage on the battlefield. Because the gas generator spins freely of the drive wheels, the engine delivers maximum output torque when the vehicle is sitting at a complete standstill. When the driver hits the accelerator, immense kinetic power transfers to the tracks instantly without stalling the engine, propelling a 70-ton steel fortress from 0 to 20 miles per hour in just 7 seconds. The tremendous energy required to generate this instant mobility carries a severe penalty in raw heat loss through the exhaust manifold. To reclaim some of this wasted energy, designers installed a massive stationary wave plate recuperator directly behind the turbine exit. This continuous flow heat exchanger channels scorching exhaust gases across complex internal metal plates, transferring heat back into incoming compressed air before it enters the combustion chamber. By preheating the intake air, the recuperator recovers roughly 20% of the thermal energy that would otherwise vanish into the atmosphere as waste heat. This thermal recovery significantly reduces the amount of fuel needed to maintain optimal combustion temperatures, extending the operational range of the Abrams. Without this vital component, the turbine's extreme fuel consumption would render long-range armored thrusts across hostile territory logistically impossible. When compared to traditional heavy diesel engines, the torque delivery of the AGT1500 reveals a stark operational difference. Standard diesels must build engine revolutions and turbocharger boost before delivering full pulling power, causing a critical lag when accelerating from a complete stop. The gas turbine reaches operating speed almost instantly, maintaining a flat torque curve that gives drivers immediate kinetic power at the tracks. This rapid response changes how crew members survive under direct fire. In combat, an Abrams driver can drop behind a protective dirt ridge, pop up to fire a main gun round, and reverse back into safety before enemy gunners can lock onto the target. That immediate surge of raw acceleration turns a massive steel fortress into an agile defender on a chaotic battlefield. To support this high-performance turbine, military leaders fundamentally reshaped supply lines in the late 1980s. The military moved away from stocking multiple fuel types and standardized on JP8, a single kerosene-based fuel for both aircraft and ground forces. Burning the same fuel as jet fighters simplified distribution networks across an entire theater of operations. This single fuel doctrine eliminated the dangerous risk of misfueling armored vehicles during high-speed tactical advances. Supply units no longer had to manage separate diesel and aviation fuel convoys through hostile territory. However, moving one universal fuel did not reduce the massive bulk volume that an entire armored brigade needed to keep moving forward. The true test of this engine design arrived during combat operations in the 1991 Gulf War. Fine desert sand and powdery silt swept across Iraq, drawn into the turbine intakes at thousands of cubic feet per minute. The microscopic grit clogged the air filters within hours, threatening to erode the spinning turbine blades if abrasive sand reached the engine core. Tank crews faced brutal physical conditions in the extreme heat, forced to stop every 100 miles to clean out the air filtration system. Soldiers pulled heavy filter packs in blinding dust storms, using compressed air to clear trapped silt while staying alert for enemy attacks. Field mechanics worked around the clock, fighting to keep engines breathing through the thick desert air. Behind this constant maintenance lay the unforgiving reality of turbine fuel consumption. Unlike a diesel engine that sips minimal fuel while idling, the AGT1500 burns nearly 10 gallons of JP8 per hour just standing still. Under cross-country combat conditions, efficiency drops further, with the tank averaging a harsh 0.6 miles per gallon. This high fuel draw created a massive logistical demand during rapid combat operations. An armored division required hundreds of thousands of gallons of fuel every single day just to maintain operational readiness. Continuous supply lines of soft-skinned tanker trucks had to follow right behind the armored spearhead, creating a vulnerable link in the operational chain. The turbine also creates severe heat management challenges on the battlefield. Exhaust temperatures leaving the rear manifold reach 900 degrees Fahrenheit, sending out a massive thermal signature. Enemy thermal optics and top-attack anti-tank missiles can easily spot this intense infrared energy against cooler terrain from miles away, making stealth difficult during nighttime operations. That extreme exhaust heat creates an immediate physical hazard for accompanying infantry forces. During urban combat operations, foot soldiers cannot take cover directly behind the tank hull without risking severe burns from the superheated air blasting out the rear. Infantry squad leaders must alter their tactical formations, keeping troops clear of the rear exhaust deck during joint maneuvers. To harness this raw energy, engineers paired the Honeywell AGT1500 with the Allison X1100 3B hydromechanical transmission. This complex drive system provides 4 forward gear ratios and 2 reverse gear ranges, engineered specifically to manage 3,700 foot-pounds of torque. It translates the turbine's high rotational speed into controlled ground speed while managing heavy mechanical stress. The transmission uses a hydrostatic steering unit alongside integral brakes and automatic power shifting mechanisms. This design allows the 70-ton vehicle to make smooth pivot turns without interrupting power delivery to the tracks. By absorbing extreme force spikes during hard acceleration, the coupling prevents catastrophic drivetrain failure and keeps the massive hull moving across rugged terrain. When armor fails in combat, the combination of extreme heat and jet fuel inside the engine bay presents a terrifying hazard. Inside that steel compartment, temperature spikes from a breached fuel line can trigger a catastrophic fire in less than a second. For the crew trapped inside the crew compartment, a fire behind the bulkhead means instant life-threatening danger. To protect against this nightmare, optical fire sensors constantly scan the power pack compartment. Upon detecting light from a fuel line rupture or shell penetration, automated valves flood the engine bay with pressurized halon gas within milliseconds. This rapid suppression smothers the flames before internal turbine heat causes secondary fuel explosions, giving 4 tank crewmen a crucial margin of survival. When comparing the M1 Abrams to peer vehicles, engine design reflects contrasting military doctrines. European heavy armor, like the German Leopard 2, uses the MTU MB 873 KA501 diesel, while Russian forces rely on the T-90's V92S2 diesel engine. European armies rejected gas turbines due to heavy fuel consumption, whereas American planners prioritized instant throttle response and cold weather starting. Looking across cold northern European forests and vast training grounds, long-term policy decisions took shape around this engine architecture. Military leaders realized that keeping gas turbines operational required massive fuel logistics networks and costly maintenance overhauls. Despite the high operational expenses, defense contracts locked in continuous modernization efforts to preserve the turbine's unique mobility advantage. On wide, windswept proving grounds, decades of field data proved that high operational costs were the unavoidable price of top-tier speed. Fleet managers established specialized depot facilities and dedicated maintenance cycles to handle turbine wear. This institutional commitment transformed supply chains, ensuring that heavy armor units maintained unmatched speed regardless of harsh environmental conditions. The human cost of maintaining this complex propulsion system fell squarely on Army mechanics and ground crews. Technicians working in remote forward bases faced grueling hours replacing air filters and conducting delicate turbine teardowns under extreme weather conditions. Their daily labor proved that mechanical excellence requires constant human vigilance and relentless physical discipline behind the scenes. Tank crews learned to adapt their combat habits to the engine's unique operational personality. Drivers had to manage fuel levels carefully during long tactical pauses, knowing that idling drained fuel tanks at an alarming rate. Military planners changed their tactical expectations, recognizing that supreme battlefield mobility depended entirely on the precise execution of supportive maintenance crews. This engineering strategy fundamentally changed how modern armies approach heavy armored warfare. A formal defense review in 2004 confirmed that despite the severe logistical burden, the turbine's cold start capability and instant power outweighed its drawbacks during fast-moving combat operations. That finding cemented the engine's role as the foundation of armored doctrine for decades to come. A comprehensive Army Materiel Command review published in 2021 underscored how this turbine architecture reshaped armored logistics across global operational theaters. Military strategists realized that deploying heavy armor was no longer merely a matter of tactical positioning on the battlefield, but an exercise in continuous fuel delivery and thermal management. By binding ground mobility to jet fuel supply chains, the decision fundamentally altered how defense planners calculate fuel consumption, maintenance schedules, and depot support requirements. What began as a bold engineering gamble in the late 1970s ultimately forced Allied coalition forces to redesign their entire forward supply network to keep pace with a 70-ton Predator. When the Abrams sits silent on a desolate desert line, its cooling turbine housing holds the heat of 1,500 horses waiting to ignite. That low, characteristic whistle of escaping air remains a stark reminder that true battlefield dominance comes at a massive physical cost. The Honeywell turbine stands as an enduring monument to modern engineering, where raw velocity and uncompromising power outweigh every operational sacrifice required to keep it moving forward across the sand.